Perfect. Then it will be okay. Okay, yeah. So often one is interested in sampling some certain probability distribution. Here I denoted it by mu, which is proportional to some exponential minus some potential u. And what we often have in mind is that this potential u might be very intractable in the sense that it might be non-convex. As you can see in this figure, it can be like a multi-well potential or like this banana-shaped potential. And then the question, then it's getting more harder to sample this probability distribution. And one possibility to do this is using, as we will see later, the Langevin dynamics. And so this was the motivation to study this, in particular also to study for this long-term behavior of the Langevin dynamics. And then this has, of course, many applications. You perhaps know more than I about this type of applications. And yeah, this was the motivation. So as I said already, I will first talk about the continuous dynamics, about the Langevin dynamics here, about the classical one and the nonlinear one. For analyzing the long-time behavior, I will use the coupling method. So I will give a short recap on couplings before I then present the contraction results, so the long-time behavior. And then I will also, as I will introduce this nonlinear Langevin dynamics, I will also talk about mean field particle models, so this model can be used to approximate this nonlinear Langevin dynamics. In particular, if we then approximate this, we can measure this type of approximation, and this is then called propagation of chaos. And as I said, in the second half of the talk, I will talk about discretization schemes. Here it's called kinetic Langevin sampler. I will have a look at the Euler discretization and then on more difficult schemes like some splitting schemes. And there again, I will analyze the long-time behavior. I will also look at how good are these discretizations to approximate the continuous dynamics. And I will also talk about the mean field particle model. Okay, so let's start with the classical Langevin dynamics. So in the very classical sense, we have a process xtvt, which is described by the second order SDE, where the position xt, so the change in the position is given by the velocity, and the change in the velocity is given by this term here, where we have minus the gradient of u. And then we have some Ornstein-Uhlenbeck part minus gamma vt plus then and some Brownian motion part. And so this first part here of this dynamic corresponds to the Hamiltonian dynamics, while the second part of the Ornstein-Uhlenbeck part. And if we look at some trajectory of this process, then we see, well, there's only noise coming in one component, as you can see here. So only the velocity part. And this actually makes it later on the analysis harder in our case. And as I said, this dynamics is often used for sampling a probability distribution, since this process has the Boltzmann-Gibbs distribution as a unique invariant probability measure. As you can see here, if now our potential u is some double well potential, we obtain something of this form. But I said I will not only talk about the classical Langevin dynamics, but also about some nonlinear type, where we have some distribution-dependent forces. And so we start again with a process xtvt, and the change in the position is again given by the velocity. And then the change in the velocity, this changes now. Instead of having here now the gradient of u, I take now some general drift b. And I have here some additional part where I have an interaction between the process itself and the law of the process, so which is here described by mu tx. And if you're more familiar perhaps with also PDEs, then this has some equivalent in the PDE community, which is just the Vlasov-Fokker-Planck equation. And given by this formula. And now the question is, if we have now this type of dynamics, this question is still, does it converge to some unique, does this dynamics has a unique invariant probability measure? And if it has so, how fast does it converge, or does it converge to it, and how fast does it converge to it? And in particular, if I have now two versions of these dynamics and the law of these I denote here by mu t and nu t, I'm wondering if I look at now the difference of these two laws of the two copies, if they are contracting to each other, converging to each other, so that I have contraction. Here I wrote it down in Wasserstein 1 distance with respect to some distance rho. This I will actually show later on. And this distance rho is hopefully equivalent to the Euclidean distance, so that we get also contraction in the Wasserstein 1 distance paying here price of getting an additional constant. So that's the idea how actually we will later on approach the long-time behavior. And as I said, we will do this using the coupling method. So if you're very familiar with coupling, then you can perhaps have a small break, but otherwise I will give a short recap on coupling. So a coupling of two measures, so not of two processes, but of two measures is just, if you have two measures, nu and eta, then a coupling of these measures is just a probability measure now, gamma on this enlarged space, on the space of probability measures on RD times RD, with marginals mu and nu. And this concept of couplings for measures, we can also translate to stochastic processes. So if you want to couple two stochastic processes, again, we consider then a process now on this enlarged space, so RD times RD. And so this process xt twiddle and yt twiddle should be such that if we just look at the law of one part of this process, now here I just had here x twiddle and y twiddle, then it should coincide with the law x and y. And as we will see later, we will see later what this exactly means for our SDE. And then I already showed this on the previous slide. I will show later on contraction and Wasserstein distance. So here I wrote again the definition of the Wasserstein distance just to recap on this shortly. So the Wasserstein distance, Wasserstein 1 distance with respect to this distance rho is just given as the infimum over all possible couplings between mu and nu of the integral of rho xy d omega. And if I just write W1, then I replace this distance rho by the Euclidean distance. So that's then often the usual Wasserstein 1 distance, which is often used. Okay, as I said, we want now to look at couplings of two stochastic processes, and here I want to give a short recap. And before I start looking at this more complicated second order SDE, I will have a short look at a first order SDE, just at this SDE where the process xt is given by this SDE minus the gradient of u, and we have some Brownian motion part. Because here we can visualize it a bit better what we are doing. And so the idea is, for example, if now u is strongly convex, so which is not the case on the pictures I showed at the very beginning. So we are more interested in non-convex u, but that's the first step. So if u is kappa strongly convex, we can just take a synchronous coupling. That means that we couple the two processes, we couple them through their Brownian motion. And here we just take the same Brownian motion as it is illustrated in this picture. And then if we look at the difference process here now squared, doing Ito calculus, then we get this term here, and then we can just plug in the definition of this kappa, or can we use the kappa strongly convexity, bounding it by minus 2 kappa, and then the distance xt minus yt squared. And then you see already using Kronwall that we get contraction here. Actually, here we get contraction for all Wasserstein distance, p Wasserstein distances. But often the problem is that we are non-strongly convex. So as it is kind of like shown here in this picture, this kappa strongly convexity drives our two processes together. We need to consider some different coupling, and this is an example for different coupling is the reflection coupling. So if we, for example, now consider a potential U, which is strongly convex outside the Euclidean ball. So this actually corresponds also to the picture we had at the beginning, where we had some multi-well potential where it can be like strongly convex at far away, and inside there might be something else. And so inside, something else can happen, but we are only strongly convex outside the Euclidean ball, which is encoded here. In this condition, then the idea is that we take a reflection coupling. Again, we take two copies, and the idea is that we reflect our coupling. And so as you can see here, this trajectory, and this is how it is then written in formulas. And we reflect it as long as these two trajectories, until the two trajectories meet, and then we take a synchronous coupling. And then indeed, we can also show some contraction Wasserstein distance. If we now look at this process RT, which is just the difference of xt minus yt, and if we now, the idea is that we consider an appropriate function f, and I will say later a few more words what our function f will be. But if we now do Ito calculus again for this process FRT, then actually we will take, well, we can do Ito calculus, we end up with this formula here. And now the idea is that we take a function f which is concave, which helps us in the sense that we get from Ito calculus, we get from the quadratic variation part, we get here a second derivative of f. And if f is concave, then this is negative. And this will help us such that the idea is that we construct this f in such a way that we can bound this whole drift term by minus some contraction rate times this function f. And yeah, as I said, well, this function f is concave, so that we get here some negative part. Additionally, we want that it's 0 at 0 and has a slope 1 at 0. And yeah, and indeed, one can construct such a function f. And then, okay, the next step is to take then expectations so that the martingale part vanishes, and then using Cornwald's inequality to get contraction in Wasserstein 1 distance with respect to this distance depending on this function f. And yeah, this then gives us contraction in Wasserstein 1 distance. So this is now the idea for this first order ST. So the hope is that we can also find a coupling for the second order ST. So for the Langevin dynamics, I just wrote here again. And let me just, before we start, let me fix some assumptions we want to consider. So first, we want that our drift term, which does not need to be of this gradient type shape, but can be something general, but you can always have this gradient type shape in mind. So we want that B is Lipschitz continuous, and we want that there exists some constant R, such that, well, the idea is that we want now to split our B in a linear term and some perturbation term. And for this perturbation term, we want that this condition is satisfied. And again, if you think of this gradient type, so if B is of gradient type, then this would correspond to the fact that our perturbation, again in gradient type, if it's also a gradient of some function, that this function is convex outside the Euclidean ball with radius r. And then this term, well, if you think again, not on the drift B, but on the potential level, then this would correspond to having some quadratic function. With now we want that this matrix has smallest eigenvalue kappa, which corresponds to this kappa strong convexity constant we had on the previous slide. And for our interaction term, we want that this is also Lipschitz continuous, and we want actually that this Lipschitz constant is rather small. Well, actually, we would like that we can also handle larger Lipschitz constant, but we will see it later on that we have to restrict this to rather small Lipschitz constant here, so that we can only consider potentials or interaction potentials, or then drift terms, which are very very small. Okay, this is the setting we are interested in. But before I present the result I did here on the second order Langevin dynamics, let me shortly recap what else is done already for this dynamics, because it has been studied a lot before I did this. So using analytical methods, here hypercoercivity is used, and then also later on some space-time dependent Poincare inequality, because one cannot use directly Poincare inequality. So the idea was to use some space-time dependent Poincare inequalities. And also I was not the first one who was using couplings to approach the long-time behavior of the Langevin dynamics. So using a synchronous coupling and being in a strongly convex case. For the classical Langevin dynamics, it was invested by Réan Durand and Dalalian, but also for the nonlinear one using the synchronous coupling, it has been studied. And let me also mention the work by Eberle, Guillen, and Zimmer. So they looked at the classical Langevin dynamics, and they used some reflection coupling we will also later use, and they constructed, and then also some Lyapunov function, and then they had constructed some semi-metric of this form here, and they could show contraction with respect to this semi-metric. And also then in a works after, this idea was used using some Lyapunov function. But I will hopefully, what I then did was, so here we had like, this is not really a metric or a distance, it's only a semi-metric, and so I aimed for getting contraction with respect to really a distance function. Yeah, and and this is what I showed before. Let me just state the result before I go into more details how we do this. So if I have now two initial measures, mu0 and mu0, and let mu_t and nu_t be this law of the two copies of the Langevin dynamics, and then I assume the set of assumptions I just presented before, so that we are somehow strongly convex outside the Euclidean ball, and that I can split this drift in these two parts, and also that and then additionally I want that I need this additional assumption, which somehow which can be understood that depending on how large our this perturbation of the drift B is, we have to choose our gamma, which is the gamma which appears in the Ornstein-Uhlenbeck part. We have to choose this sufficiently large, so that it means that we need sufficiently much noise coming into our system, so that the Ornstein-Uhlenbeck part has to be sufficiently large. Then I can construct a distance rho such that we get contraction in Wasserstein bond distance with respect to this distance. And here the contraction rate C is in particular is independent of the dimension, and it depends only on our friction parameter gamma, on this convexity constant kappa, on the Lipschitz constant of the perturbation, and on R, which was this parameter where we are strongly convex outside this Euclidean ball. So this was this radius. And in particular, if we now in the strongly convex case, so if R would be 0 or even more, if our potential U is just some quadratic potential, we can write down our contraction rate explicitly of this form. And then this is maximized or optimized, maximized, if we choose this gamma. So in this case, we get a contraction rate of square root of kappa over 4. And so let me now talk a bit about the proof. I already said we will use the reflection coupling of the work by Eberle and Sidmar. And here the idea is, if we now look at the two copies and look at the difference space, so here the difference of the position and the velocity, the idea is that we will, if you look at this difference space, that we handle, depending where we are in the space, we handle it differently. So the idea is that we will consider two different types of distances. The first one is some twisted L2 distance, which somehow, well, the level z corresponds to this blue ellipse. And then we will also look at some L1 distance. So this is this green rectangle. So there's the level set. And the idea is that we will can show contraction outside this blue ellipse using either some synchronous or reflection coupling. And then we will also show contraction inside this green rectangle, and then kind of like combining these two results and gluing this two distance in a nice way together, that we then get contraction. As I said, so we have like a distance RS. This is what I said with this L1 distance, and this RL, which you use for large distances. This is some type of twisted L2 distance. And then I said, okay, we have to glue these two distances, RS and RL, in a very nice way together. And additionally, we will use the idea I presented already for the reflection coupling in the first order case. We will also consider some concave increasing function f. And then you can kind of like glue this in a very nice way together. I don't want to be here too precise on the details, but the idea is mainly that we just go back, that we have like a transition from this distance RL along to this distance RS along this deformed red rectangle. And we take outside of this deformed red rectangle, we take a synchronous coupling. And here we can use then the strongly convexity property if we are large enough with the distance, or we can, or in combination with the Ornstein-Uhlenbeck part in the dynamics, to get then contraction for the distance RL. And then inside this red rectangle, we use the reflection coupling, which was already considered by Eberle-Guillen and Zimmer in their paper, and a concave function f, such that we get then for this process FRS, we get also contraction. And then the idea is gluing these two distances together to this distance rho, taking expectations so that the martingale parts, the dmt1 and dmt2, are vanishing, and then using Kronwall to get then contraction with respect to in Wasserstein distance with respect to rho. This we can now do for the classical Langevin dynamics. And now if the nonlinear Langevin dynamics comes into place when we have this additional interaction part, then we get here some additional drift terms. And that's why we have a very strict condition on the Lipschitz constant for the interaction part. The idea is here now that we take this Lipschitz constant L twiddle sufficiently small such that here we lose then half of this contraction rate somehow. And so with this, we get then also contraction for the nonlinear Langevin dynamics. And as I said at the beginning, so this nonlinear Langevin dynamics can be approximated by some particle model, so by some mean field particle model with n particles. Here, the idea is that we have n particles, and each particle is also driven by this Langevin dynamics. And instead of having here the interaction between the process and the law of its process, we have pairwise interactions between the particles. And with this, we can actually also prove convergence between or propagation of chaos, it's called. So if we now start, if we have now n independent, this one, n independent copies of our nonlinear Langevin dynamics and compared to this n particle system, and if we start both with the same initial condition, we can actually show that the distance between these two laws can be bounded by n to the -1/2 times some constant c, which is independent of the time small t. And here, this distance we consider here is now here's this average L1 distance. And how we do this, here the idea is again similar as we have done for the contraction result. We will look again at the same coupling now here for this all this. So here we look at the particle-wise adaptation of the coupling. So each particle is coupled to the corresponding particle of the other copy, as we have done it before. And here the idea is if we have now here this nonlinear Langevin dynamics, that we add here these two terms, so plus minus 0. And then the idea is that we now look only at the two copies, and for the first copy we just consider, instead of this integral term, we can just consider now this term of this interaction term, and so that then for this, if we now just look at this term, we can actually also show contraction with some rate with the same contraction rate c as we had it before, and so we only have to control this term and this term here, which as I wrote here. This can be done by the second moment bound. So so if we look now at the difference of these two copies, we can bound it by the Lipschitz constant of the interaction force and the second moment bound, and we can actually get a uniform second moment bound. And then we can get finally uniform in time propagation of chaos. As I said, so we need a uniform second moment bound, and again, as before, we use then Kronwall's inequality to end up with this equation, with this bound. Okay, this is everything I wanted to say about the continuous dynamics. So now the question is, since we want to sample, or often one is interested in sampling some probability measure, we need also some discretization scheme to be able to be able numerically to sample it. And so, as I said, this is called a kinetic Langevin sampler, and here perhaps easiest way to discretize our scheme is using a forward Euler scheme. So we have now a Markov chain x, k, and vk, and so then the update of x to the next state, xk plus 1 and vk plus 1 is just via this form here. Here I again switched back now to the classical Langevin dynamics. And well, for this scheme, we have that the scheme has local error of order 3/2 and global strong error of order 1. But we can also consider more or more complicated schemes. And this, yeah, here I said one can use splitting schemes. And so the idea is, if we have now look again at our continuous dynamics, that we now split this SD in different parts. So here we have, for example, this Ornstein-Uhlenbeck part. And then we have this here, this part I called B, and here this part A. And each of these parts can be integrated exactly over time. And then the idea is that we then combine this. So, for example, if we have this, now this, we have some interesting words to call these schemes. But this, for example, Bauer scheme is like we do, if we have the discretization step H, then we do one step B of size H/2, an A step of size H/2, a step O of size H, then a step A of H/2, and a step B of H/2. And so this type of splitting schemes, or these numerical methods, now are of weak order 2 and still of a strong order 1. And in particular, let me also just mention, so for this Obabu scheme, there was already the long time the long time behavior analyzed in this paper by Chuck and Montmarché. But we can also split it differently, and that's the scheme I will look at in the following. So-called UBU scheme. So we have again our part B, and now we combine this A and O part to part U, and this can still be integrated exactly, but the formula is getting more complicated. And the nice thing is that this scheme has now strong order 2, and one needs only one gradient evaluation per step. And if we look a bit closer to this UBU or BU scheme, well, then this can be written down explicitly. These are clear formulas you don't have to remember. Just let me mention 2 things. So, well, this is just our B and our U step. And for U, we need now, so for the Euler discretization, we had like the noise term or the Brownian motion term was represented by some normally distributed random variable. Here for this UBU scheme, or for this U step, we need like 2 normal distributed random variables, psi and theta. And then you can write it down explicitly how you integrate it exactly. And so then kind of like you get, if you have like your Markov chain and you have your state x, k, and vk, then you get your step xk plus 1 and vk plus 1 by doing then here in the UBU scheme, like again, first a half step of U, a full step of B, and a half step of U again. And in particular for this UBU scheme, then you have already 4 random variables, which we will need later for analyzing the long time behavior. And before we do this, let me again now also fix here the assumptions. So they are similar to the one I had in the continuous dynamics. Now I just wrote everything with the gradient type again. So we were looking at this gradient of U. This we want that's again Lipschitz continuous. And again, we want U to be kappa strongly convex, also at the Euclidean ball. And indeed, this can also be now rewritten by kind of like splitting our potential U in 2 parts, in this quadratic part and then this perturbation part. And this perturbation part should be convex, and this quadratic part with this positive definite matrix K should have the smallest eigenvalue kappa corresponding to this kappa strongly convexity constant. And then we will use now a coupling again to analyze the long time behavior. And here, just let me explain it for the Euler discretization. So we have again, now we will look at 2 copies with initial conditions x, v, and x prime, v prime. And then the next step is given via using the initial conditions x and v, and then we have a standard normally distributed random variable xi. And then here the idea is that we couple now these two copies via coupling our two variables xi and xi prime in such a way, well, that this pair of random variables is now defined on a common probability space, and both have are standard normally distributed random variables. Again, here the aim is that we want to find a distance rho, and again a coupling such that we have in one step we get contraction. And we do this similarly as we have done it in the continuous dynamics. So you see again this picture of where we look at the difference process. And here again, the idea is that we will split this space in different areas. And again, outside this deformed red rectangle, we will take a synchronous coupling, while inside this red rectangle, we will take not directly a reflection coupling, but this type of coupling, which was already used for analyzing, for example, the Hamiltonian Monte Carlo dynamics, but also it was used in the paper by Chuck and Monmarché when they analyzed the Ovabo scheme. And let me just mention that if now our discretization parameter h goes to 0, then we end up with the same, or this approaches the coupling we were considering in the continuous dynamics. And as before, inside this rectangle, we will have also to consider a concave function f, and then for this inside this rectangle, we can use then this concave function f to get a contraction there. And then the idea is again to combine these two distances such that we get then a contraction on the full space. And in particular, so if we are in the situation that under the assumptions I presented previously, so that we are Lipschitz that the gradient of view is Lipschitz continuous, and that we are strongly convex outside the Euclidean ball. And then we can, if we have mu k and nu k, the laws of the two Euler discretizations. And if we additionally have again that our Ornstein-Uhlenbeck part, or the discretization of the Ornstein-Uhlenbeck part, but here, so that this friction parameter gamma is again sufficiently large, and then we have also some condition that our discretization parameter has to be sufficiently small, then again we can find this distance rho such that we have contraction with respect to this, that we have contraction Wasserstein distance 1 with respect to this distance rho. And again, this distance rho will be equivalent to the Euclidean distance, which gives us then a contraction Wasserstein distance 1, paying here a price of getting some additional constant m. But both the contraction rate and this constant m are independent of the dimension and also independent of our discretization parameter h. And yeah, again, I said, well, we do this coupling construction, distance construction, such that we get contraction in one step. And let me just mention here, we did now here the case that we are outside, that we are strongly convex outside the Euclidean ball. For the strongly convex case, this was done already by Langevin, Pauline, and Peter Wally. And again, we can have a look at the contraction rate, and here we get similar to the continuous dynamics, we get a contraction rate of order squared over kappa. So this was now done for the Euler scheme. We can do the same for the UBU or BU scheme. So let me just present it here now for the BU scheme, because for the UBU scheme, we will later on use a trick. And here, as I said, here we have like now two random variables, xi and theta. And here we will couple xi in a similar way as we, or in the same way as we have done it for the Euler scheme, while for the variable, the random variable theta, we will take a synchronous coupling. And then again, under similar assumptions, so that gamma is sufficiently large and our parameter h is sufficiently small, then we can get also contraction for the BU scheme with, again, with some contraction rate c twiddle and constant m independent of d and h. And then the idea is now we want to move to the UBU scheme, that if we now consider like a case step of our UBU scheme, we can now split it in a nice way, such that we kind of like the middle part we can handle using the contraction result, and for half a U step or a B times half a U step, we can just control these steps, so that we control half a u step, we can control it by 1 plus some h times some constant, and the same we can do with the bu half step. And then if we combine this, then we see that we get a still contraction. But if we now look at the theorem, but again, now paying here price of getting an additional constant. But if we do sufficiently many steps, then we still get contraction. Yeah, and actually we also did some numerical simulations here at this for the banana shape distribution I showed you at the very beginning. Here on the left-hand side, it's a normal scale, while it's on the right-hand side, it's a log scale. But you see here for different types of gamma, we did the synchronous and the reflection coupling. And in particular, if gamma gets small, then we see that we are doing better with the reflection coupling than with the synchronous coupling. And now we have done the long-time behavior. We analyzed the long-time behavior for the discretized scheme. The question is now, how good do they approximate our continuous dynamics? And this can also be done. So if we now denote by mu infinity our true target measure, or the Boltzmann-Gibbs distribution corresponding to our continuous Langevin dynamics, and mu h infinity the invariant measure of the Euler discretization, then what we can actually do is we can bound the distance between these two measures by h times square root of d for the Euler discretizations. And let me just shortly mention how this is done. So if we look here at the distance of the two measures, we will well, we can just ask, since they are the invariant measures for both the discretized and the continuous dynamics respectively, we can just add these, and then we do some triangle inequality. So we add here mu infinity, and then PHL is the transition step of the Euler discretization after L steps of the Euler discretizations. And then for the second term, we can just use our discretization, we can just use our contraction result for the Euler scheme. So we can bound this by 1 minus h times c to the power of L. And then we can now put this term on the left-hand side, and then we get, we can bound it, the distance between mu infinity and mu h infinity, we can just bound by starting in mu infinity and doing L steps of our, either of our continuous or discretized dynamics. And this actually can be bounded, this term, by h times square root of d, if we take L such that L times h is of order 1. And then we get, with this we get then this bound between these two invariant measures. And having this in mind, we can now, if we start in some measure nu and we run for k steps our Euler discretization, we can give a we can bound the distance between this measure after k steps and the invariant measure of the continuous dynamics by, again, doing some using a triangle inequality. And then for the first term, we can just use our contraction result, while for the second term, we can just use the strong accuracy result we had on the previous slide. And so we see that if, for example, we want that this distance is smaller than epsilon, we know how we have to choose the number of step size and the discretization parameter to become smaller than epsilon. And the same can also be done for the UBU scheme. We can also get complexity guarantees for the UBU scheme. Again, since we can bound the distance between the invariant measure of the continuous and the discrete dynamics by h times square root of d. Or if we have some additional regularity, we can actually bound it by h squared times square root of d. Yes. Yeah, let me now at the end shortly also go to the particle system. So I said already before, we use the particle system to approximate this nonlinear Langevin dynamics. Here it's again this short recap. So we have now, we want to approximate our measure mu, satisfying this equation by a particle system, where we have now this potential un consisting again of some confining potential or external potential, and then some interaction potential. which again, if we write down the Langevin dynamics, corresponds to the continuous nonlinear continuous Langevin dynamics and this mean field particle continuous Langevin dynamics. And as we had before, this is just a recap on the uniform in time propagation of chaos results. So we can bound the distance between the laws of n copies of the nonlinear dynamics and the n particle system, independent of time. And additionally, what we can also do is we can also bound the invariant measures mu star and mu n infinity. And then the idea is that, well, again, in the particle model, we can also get then complexity guarantees for the Euler scheme. If we then want to know, okay, how many steps do we need to get close to our invariant measure? This is actually the same as we have done for if we would just have one particle, but we can also compare the distance of our n particle system to the invariant measure or set of for the nonlinear Langevin dynamics. And here we get just some additional term we can bound by our result for the uniform in time propagation of chaos. And this in particular gives us shows us that how we need to choose our number of the number of particles, the step size h, and the number of steps, such that we get epsilon close to our desired target measure. Yeah, and in particular, the first two terms are independent of n, and only the last term coming from this propagation of chaos result depends on n. Yeah, and that's actually all I wanted to present today. So we have seen we have some contraction result for the Langevin dynamics, both for the classical and the nonlinear one, and we also analyzed some discretization steps, and I'm happy to answer now some questions. And also, if you want at some later point or want to ask some questions, just you can just send me an email and we can discuss on it. And these are the two papers I mainly presented today. And of course, there's tons of other references I mentioned during the talk, and obvious and many more. And yeah, that's it. Thanks.
So thank you very much for the talk. So I would like to ask if there is some questions or comments.
Yeah, thank you very much for a very nice talk. Maybe just a question on the noise term. So you had in I think all of you all the results you mentioned, you had some conditions on that the noise should be large enough. Could you say a word whether these are necessary, or in particular in the strongly convex case, if you would expect any sufficiently noise condition?
Indeed, it's something which also yeah, I'm not very satisfied with. So it's for the Gaussian case. So if you have just a quadratic potential, then we don't need any condition on the noise term. So we can just take any gamma. In particular, we can let gamma go to 0. While as soon as already, if you have just a kind of a small perturbation of this quadratic term, we already need this condition. And as far as I know, I think in also all on these on the papers. Interesting. I think also in many other papers, this condition on the noise term is needed in the strongly convex case, except I think, let me just go back to the list of references. I think when in the paper on this space-time dependent Poincare inequality, while they showed it in a different distance, there they don't need this condition. But yeah, there it's a completely different, it's a completely different distance and a different technique. But I think even in this, I don't know exactly all of the papers, but definitely in this paper by Achleitner, Arnold, and Stürzer, they have also this condition on gamma. I think it's not exactly the same condition, but it's also that they have a lower bound on this friction parameter gamma.
Thanks.
Yeah, but it would be nice to get rid of it because, well, I think actually, or my hope is somehow that one can get rid of it, but I don't know how.
Are there more questions or comments? If not, I would like to ask some question. Are you able to get bouncy in total variation distance?
I haven't looked at this, to be honest. It's something one should definitely consider, but I haven't done it.
And another question, if you replace the Brownian motion by alpha stable noise, can you apply similar techniques just to compute, I don't know, moments less than alpha? No?
Mhm. Yeah, to be honest, I don't know how one is actually constructing in this case this coupling type things. So I think this is so I haven't looked at this scenario, but I think one needs to understand how this coupling techniques would work out there, or whether it works out there. I don't know.
Okay.
I haven't had a look at it.
Okay, perfect. Okay, are there more questions or comments? It seems no, so let's thank the speaker again, please. And thank you for the talk. And I think we met next week.